So we've been talking about some things that have to do with our functions and our derivatives. We talked about the mean value theorem, which told us that the derivative has to be equal to our average slope at some point. We also talked about Raleigh's theorem, which started kind of bringing in a derivative being zero. We said that, hey, if we have our endpoints the same, then we have to have the derivative equal zero somewhere in that interval. Then we looked at some graphs and said, hey, notice that our derivative is zero if we have a maximum or a minimum. We also looked at how we find critical numbers, and the critical numbers were where the derivative was zero or undefined. So now let's kind of put that all together. Let's talk about where, well, all except for maybe the mean value theorem. Let's talk about where can we find extrema on a closed interval. And what we find out is that even though Raleigh's theorem tells us if our endpoints are the same, we'll have a maximum or minimum somewhere in that interval, we can have maximums and minimums even if our intervals or our endpoints are not the same. What we use is this relative extrema theorem, and it tells us that if a relative minimum or if a function has a relative minimum or a relative maximum at some x value, that x value has to be a critical number of f. However, just because something is a critical number does not always mean there's an extrema at that point. For example, if I look at my x cubed function, notice that's not a very good drawing. Let me try to draw that better. And also I'll take up some space over here. Notice if I look at my x cubed function, isn't my derivative going to be zero right here because doesn't it flatten out there right in the middle? However, notice I do not, when I look at my graph, I do not have a maximum or minimum there in the middle. So even though I could set this equal, I could find the derivative and set it equal to zero, even though I would have a critical number at x equals zero, I do not necessarily have a maximum or minimum there. So if just because I have a critical number doesn't mean there's an extrema, what can I do to find extrema? Well, here's the guidelines I'm going to follow. I want to first find my derivative, then find all my critical numbers, then I'll plug both my critical numbers and my endpoints back into my original equation, and whichever of those gives me the smallest value, it's my absolute minimum. Whichever of those gives me my largest value is my absolute maximum. So let's look at some examples. So let's look at example 1. So I'm given this function. I'm on a closed interval from -1 to 1. Well, according to my steps, the first thing I'm going to do is find f prime. So I'm going to go ahead and say f prime of x is polynomial, so I can use the power rule. So I'll bring the 4 down. 4 times 1/2 is 2x cubed. Bring down the 3 plus 3 times 2/3 is 2x squared. The constant 4 goes away. So here's my derivative. So now I need to find all critical numbers of my derivatives. Well, I can find my critical numbers by setting my derivative equal to 0. And at the same time, I'm going to go ahead and factor my derivative because I see I can take a 2x squared out. And I'll be left with x plus 1. So since these two things multiply to be 0, either 2x squared has to be 0 or x plus 1 has to be 0. So solving the first equation, I can solve that x equals 0. Solving the second equation, I get x equals -1. So I'm going to check my endpoints and my critical numbers. Notice that one of my endpoints is a critical number. I only have to check that once. So I think it's easier if I stay more organized and make a table. So I'm going to go ahead and make my x tables and find my f of x or my y values. So I'm going to go ahead and check -1, 0, and 1. So plugging -1 back into my function, I'm just going to go ahead and use a calculator to figure out what value I get. I get 23/6, which is approximately 3.833, because I may need to see that in decimal form to get a better idea of what that y value is. I'm going to make my graph a little bit better here because I don't have enough room here. So I'm going to put my 0 here and maybe my 1 down here. So I'm going to go ahead and plug 0 into my function. When I plug 0 into my function, I just get 4. Easy enough. When I plug 1 into my function, I get 31/6, which is approximately 5.167. So now I can go ahead and determine what was my, using step 5, what's my smallest value, so what's my minimum, and what's my largest value, so what's my maximum. Well, I notice that my smallest value is right here, and my largest value is right here. So I'm going to go ahead and say I have an absolute minimum at the point -1, 23, I think that's 23/6. I wrote over it. and I have an absolute maximum at 1 and 31 over 6, giving it in the exact form as opposed to my approximate form. Looking at example 2. Example 2, I'm going to do the exact same thing. If I remember right, there's 3 examples. So if at any point you want to pause the video and see how you can do, both examples 2 and 3 are excellent opportunities for you to do that. So my steps are going to come off, but if you printed out the template, you should still have them on your page. I'm going to do the same thing. So first thing I'm going to do is I'm going to go ahead and I'm going to find my derivative. So then I can find my critical numbers. So again, I can use the power rule. So I get y prime equals 2. The 2/3 comes down, so 2/3 times minus 3 is minus 2x to the negative 1/3. Well, that's the same thing as 2 minus 2 over x to the 1/3. I'm going to set my derivative equal to 0, and I'm also going to get a common denominator when I do that because it makes it much easier to solve than that numerator for when it equals 0. So I'm going to say 0 equals multiplying 2 and 1 by x to the 1/3, so I get 2x to the 1/3 minus 2 all over x to the 1/3. So now I can go ahead and solve this equation. So because now I have a single fraction, I can say that a fraction equals 0 whenever just my numerator equals 0. So I can add 2 and divide by 2, and I get x to the 1/3 equals 1. So I can now cube each side, and I get x equals 1. So there's one of my critical numbers. My other critical number, remember, is going to be where my derivative is undefined. Notice that if x were 0, it would make my denominator 0, which would make my derivative undefined. So I'm going to use these as my 2 critical values, or my critical numbers. So now I have my critical numbers. I also have my endpoints. So I'm going to go ahead and use all that information to make a table. So these are my x values, and then my corresponding y value. So the first x value, I tend to go in order, but it doesn't really matter. Negative 1, well, when I plug negative 1, gives me negative 5. So I got my first endpoint. If I plug 0 in, 0 gives me 0. There's the 0. I'm going to plug 1 in. And when I plug 1 in, I get 2 minus 3 is negative 1. And then I'll plug my last endpoint of 3 in. And when I plug 3 in, I get 6 minus the 3 times the cube root of 9, which is approximately negative 0.240. Again, always going to 3 decimals. So now I can go ahead and say, where is my biggest value? Where is my smallest value? Well, I notice that my least value is going to be here, and my greatest value is going to be here. So I can say I have an absolute minimum, I'll start with my smaller one, at negative 1, negative 5, and I have an absolute maximum at 0, 0. And finally, looking at the last example, I would definitely encourage you, if you haven't tried one on your own, to try one on your own at this point. And the first thing I'm going to do is find my derivative, so unfortunately I have to use the quotient rule here. So the derivative of my first is 4x. Or sorry, my first is 4, my derivative of my first is 4. My second is x squared plus 2, so the derivative of my second is 2x. So h prime of x is equal to the derivative of the first times the second, minus the derivative of the second times the first. 2x times 4x is 8x squared, all over my second squared. So I end up with h prime of x equals 4x squared minus 8x squared is going to give me a negative 4x squared plus 8 all over x squared plus 2 squared. So I'm going to go ahead and set my derivative equal to 0. I know that when a fraction equals a 0, that means the numerator has to be 0. So I'm going to ask myself, when does negative 4x squared plus 8 equal 0? Well, then when does negative 4x squared equal, and I'm going to go ahead and do this in one step because I'm running out of room here. So I'm going to minus 8 and divide by negative 4, and I get x squared equals 2. So I get 2 critical numbers. I get critical numbers of plus or minus the square root of 2. And then I ask myself, when is my denominator undefined? Well, this is never going to be 0 because I'm not going to be able to square anything to get negative 2, which is what I would need to add to the 2 to be 0. So I'm going to go ahead and set up my table so I can check my endpoints and I can check my critical numbers. So I'm going to plug in x and see what h of x gives me. So I'll plug in -3, and when I plug in -3, I get -12 over 11, which is approximately -1.091. So I'll plug that in. I'll plug in the negative square root of 2, which is negative square root of 2 as well, which is approximately 1.414. I will plug in my positive square root of 2, which also gives me the square root of 2, which is approximately, I forgot my negative up here, probably because I can't see it, which is approximately positive 1.414. And then finally I'm going to plug in my last endpoint, which is 2. Plugging in the 2 gives me 4/3, which is approximately 1.333. Notice I left all the algebra out of me plugging in, so if you want me to go through that with you, please let me know. But then I pick my maximum value. Here's my maximum value. Here's my minimum value. So last thing I do is I have a relative minimum. Sorry, it's not relative. We're not there yet. I have an absolute minimum at the point negative square root of 2, comma negative square root of 2, and I have an absolute maximum at the point square root of 2, square root of 2. And that is it for finding absolute minimums and absolute maximums on a closed interval.